Hello and welcome all to the fourth video of the HAPRA and Vhdl crash course playlist. This is Sanad once again, and in this video we are going in more depth and details regarding the Vhdl language, introducing new concepts that will really help you be able to understand Vhdl. This video is a really important part of our progress, so in case you didn't understand a section from the video, kindly repeat it or search for online sources to further better your understanding and knowledge of the Vhdl and HAPRA module. In this video, we will first discuss the operational levels of Vhdl in comparison to other programming languages. We will also talk about the difference between signals and variables. Another topic in hand for today's video will be about delays, and finally, we will discuss simple sequential statements in Vhdl, such as the if statements and the loops. Firstly, the operational levels in Vhdl. In a digital circuit, all components and subcomponents operate simultaneously. For example, a gate contained in the circuit provides its functionality continuously, parallel to the functionality of other gates contained in the circuit. With a sequential programming language like C++, Pascal, or any other sequential programming language, only one instruction is executed at a time. Therefore, a sequential programming language is not suitable for the description of circuits and systems with temporary parallel processes and events. The Vhdl programming model assumes that all instruction in the architecture descriptions run simultaneously. This parallel operating level is called the concurrent level. In addition to this parallel operating level, Vhdl also offers the option of sequentially describing algorithms on the sequential level, similar to other programming languages. Signals versus variables. All in all, signals and variables are important concepts in any Vhdl program, but there may be a few differences between them both. And in this section of the video, we'll discuss the differences so you know when to use signals and when to use variables. Firstly, signals can exist anywhere. For example, signals can be handled as wires, whereas variables can only exist within a process. Signals connect components or transfer information between processes, whereas variables behave like local variables, like any high-level programming language. In a process, the value is updated when the process is stopped, whereas in variables, the values are updated immediately after the assignment, where the order is important. In signals, we use the operator of less than or equal for the signal assignment, whereas in variable, we use the colon followed by an equal sign for the variable assignments. Variables can only be inside processes. Signals can be used inside or outside processes. To re-emphasize, any variable that is created in one process cannot be used in another process, whereas signals can be used in multiple processes, though they can only be assigned in one single process. Variables need to be defined after the keyword process, but before the keyword begin, and signals are defined in the architecture declaration before the begin statement. Variables that are assigned immediately take the value of the assignment. Signals depend on its combinational or sequential code to know when the signal takes the value of the assignment. Last point of discussion would be that signals act as wire or buses and can act both as inputs and as outputs. Signal assignments represent the basic instructions in Vhdl. With their help, a value can be assigned to a signal. Signals transmit information between processes and are responsible for networking the entire designs. Both variables and signals have important function in a VHDL program, but signals are one of the most important building blocks of an efficient and clear VHDL model. This is the format of a signal assignment, where the signal takes the value using this operator. We will now talk about another function available in the IEEE library and the building block of a VHDL program, and this is the delays. In VHDL, the user has the option to carry out a signal assignment after a time unit and to implement the delay in the assignment. When modeling digital circuits, delays must always be taken into account. In real integrated circuits or in real circuitry, there are sometimes outstanding transactions scheduled for a signal when a signal assignment instruction is executed. Delays can be the best way to handle these pending transactions. There are two types of delays in VHDL, and those are the transport delay and inertial delays. Transport delays is used to model delays inserted through a wire connection or a PCB connection, whereas inertial delays models the delays integrated by analog ports. This means that it corresponds to the delay in devices that only react if the signal value is retained at their inputs for a certain period of time. Let's now go more in depth in the transport delays. The transport delay, please note that the transport delay is not the standard implemented in VHDL and must be specified with reserved words. So in order to execute a signal transport delay, we have our signal, which takes the value we assign it to, and we have two keywords included if we want to implement a transport delay, and that is transport, that comes before the value, and after the value comes the keyword after, and this represents a period of time, either in seconds, nanoseconds, picoseconds, whatever you want it to be. The inertial delay, on the other hand, is the standard implemented in VHDL, since its behavior of the delay is similar to the behavior of the device. And this is how you do a signal value after time. So basically, you have your signal, which takes the value, but only after a period of time. Once again, this can be nanoseconds, milliseconds, seconds, picoseconds, and whatever. We will now get into another topic of discussion, and that is sequential statements. Please always keep in mind that sequential statements, such as an if statement or a loop or whatever, should always be used inside of a process or a function or a procedure. So this code implemented here should always be inside of a process. The simplest if statement has the format shown on the current slide. You can spot the similarities between VHDL and any other language, including Java. Here we have an if, and then we place our condition between if and then, and if the condition is met, then we do any kind of sequential code or statements. If the condition 1 is not met, then we move to the else if, where we have another condition, followed by a then, followed by sequential statements, and finally, if both the first condition and the second conditions aren't met, Then we move to the else statements where we execute some sequential statements. And finally, we end our if statement. This is an example. The if statement on this slide has no apparent functionality, but is only a simple example of how we use it. We have condition and another condition. You can place more than one condition, of course, like any other language. So if x is equal to 5 and y is equal to 9, so if this is true and this is true, then we execute this signal assignment. Else, if x is greater than 5, then we execute this. And if x isn't equal or greater than 5 and y isn't equal to 9 at the same time, then we will execute this signal assignment. And finally, we end our if statement. Another sequential statement in VHDL is the when else. I just want to reiterate one point. Sequential statements such as these shown on this slide should always be used inside of a process, a function, or a procedure. A when else is basically the following. We have our signal that we are going to save the assignment to. So basically, signal B takes the value of 1000 when and only when A is equal to 0, 0. When A isn't equal to 0, 0, B will take the value of 0, 1, 0, 0 when A is 0, 1. Similarly, B will take the value of 0, 0, 1, 0 when A is 1, 0. And finally, if none of these three are executed, then B will take the value of 0, 0, 0, 1 when A is 1, 1. I think it's clear and coherent and doesn't need any further explanation. Another variant of the when else statement is what is shown on the right side of the screen. So we say, using the keywords with A, select B. So basically B takes the value of 1000 when A is 0, 0. B takes the value of 100 when A is 0, 1. And B takes the value of 0, 0, 1, 0 when B is 1, 0, when A is 1, 0. And finally, the same exact thing for the last statement. Similar to a case switch in Java, a case statement is also available in VHDL. As you can see here, the case statement is implemented inside of a process. And we begin the process. And with A, we emphasize that when A is 0, 0, then B takes the value of 1000. When A when the case is that A is 0, 1, then B will take the value of 0, 1, 0, 0, and so on. Finally, we end the case and we end the process. We will now discuss loops in VHDL. If statements are to be executed several times in a row, they are implemented as a loop. Please also note that loops are sequential statements and are once again used inside of a process, function, or a procedure. The format of the for loop in VHDL follows the following structure. We have a loop name, but does not necessarily have to be available at all times. And we have a for keyword followed by the loop variable in range loop. This means that in this example right here, for our loop variable in 0 to 3. That means that it will loop 3 times. Once it reaches the value of 3, it will go out of the loop. What happens here is basically we have an entity called Vorschleife, and in this entity we have two port names X and Y, where X has the mode type of n and a type of integer, and ranges between 0 to 3. So it can't take values any other than 0, 1, 2, and 3. Whereas the Y is an out and is a type of bit vector and has the size of 4. So basically 0, 0, 0, 1 or 0, 0, 0, 0, any possible combination of a 4-bit. And we end our entity declaration, and then we start our architecture declaration. We have a name for our architecture of our entity, and the behavior is the following. We begin a process and we give the value of Y zeros, and we perform a for loop for I in 0. So from I equals 0 to I equals 3 loop. We have a sequential statement inside of our for loop, which is also possible in Vhdl. And this has no apparent functionality. It's just an example to show you how it works. So when X is equal to I, then the value of Y in the position of I will take 1. So basically, if we have, let's say X is equal to 2, and we reach the for loop in the third iteration where I is equal to 2, then and only then, if X equals to I, in our case X equals to I, then Y will become 0, 0, 1, 0. We finally end our if statement inside of our loop, and we end the loop, and finally we end the process, which has the sequential statements inside of it. And we end the architecture declaration using the end keyword followed by the architecture name. We also have a while loop. On this slide, a simple while loop on the left has on the left, the format of a while loop is shown, while on the right, there is a small example of a while loop implemented. We also have a loop name, which shouldn't always be available or written. We have while and have a condition. If this condition is met or stays met, we implement these statements, and we finally end the loop followed by the loop name. Once again, loop name shouldn't always be written. So we have a process is, and we define a variable inside of the process. We name the variable I of a type integer and give it the value of a 0. As you can see here, this is used for variable assignment, where we give I the value of 0. Moreover, we begin our process, and once again, variables are declared before the begin inside of a process, like the example shown in front of you. So we have a variable that is declared inside of a process, but before the begin of a process. Moreover, we have our while loop and our condition I is less than 10, and we loop. We give I the value of I itself plus 2, and we end the loop. So this loop will basically loop either 4 or 5 times. And finally, we end the process. This wraps our video for today. I hope you have benefited from this lecture. In the next video, we will most probably go into clocks in VHDL, or actually we are going to implement our own our own VHDL program from scratch. We will implement, we will draw the integrated circuits, we will implement the VHDL code, we will also do the truth table, and we will analyze the, we will perform a wave function and analyze the wave function as well. Thank you for your attention. This is Sanad once again, and until next time.